guys, so this is problem number 65 from chapter 4 from the section on Thevenin and Norton equivalent circuits. So a Thevenin equivalent circuit basically says that if you're looking, if you take like from a wall outlet, a point of view, and you can reduce an entire circuit basically into one power source, so some voltage and some equivalent. So you can basically simplify a circuit into a single power source and a single resistance, and that's really cool because we don't always really care about what's going on inside a circuit. Sometimes we just care about what's happening at the wall outlet or some point of view, and what is happening in there is not something that we care about. So that's a Thevenin equivalent circuit, and to find its Norton equivalent we just do a source transformation, and then so we wanted to express that in terms of a current source. We could do that, so just do simply a source transformation. So to find the Thevenin equivalent circuit, we could do either the mesh current method or the node voltage method to find the power source at the point of interest seen by the load, and then and then to find the I short circuit or our Thevenin, we can open the power sources. So we can remove the power sources. So in this case, we would short the voltage sources and open the current sources, and see what resistance is seen by the load. So that's how we could find our Thevenin that way. And then the third way that we can find our Thevenin is to short the load, find the short circuit current, and then we would apply Ohm's law and say that our Thevenin is basically V Thevenin over I short circuit. So those are the ways that we have for finding our Thevenin. So we have two options for finding our Thevenin. First, option one is to find V Thevenin and I short circuit, so which is the voltage drop across the point of that's seen by the load, and then divide that by the short circuit current, which is we're going to short the load and find what is the current going through the load when we short it. So that's one way to find our Thevenin. The second way to find our Thevenin is to eliminate the power sources. In this case, we would short the voltage sources and open the current sources, and then see what resistance is seen by the load. So, okay, so that's basically the Cliff's notes on Norton and Thevenin equivalent circuits. So having said that, in this problem, we're supposed to find the Thevenin equivalent circuit. So again, a Thevenin equivalent circuit is going to be some voltage, Thevenin voltage. So that's going to be the voltage seen by the load in series with our Thevenin. That's what we are looking for in part A. In part B, we're going to find our Thevenin the number two way. The number two way is we're going to short the load, open the current source, short the voltage source. So we're going to eliminate the power sources by shorting voltage sources and opening current sources, and then looking at what resistance is seen by the load. So here we have a load AB. We're looking in here, and we're looking with respect to that 60 ohm resistor. So let's take a second to describe the circuit. I have a 9 volt independent voltage source, and I have 5 ohms here, 25, 10, 60, a 1.8 amp independent current source, and a 20 ohm resistor. And the load is right here at points A, B. So across the 60 ohm resistor. And in part A, we want to take all of this and this whole thing, this mess here, and reduce it into one simple Thevenin voltage, V Thevenin, and then in series with one resistance as seen by the load. So we're going to do that. We have two options. We're looking for this right here, V Thevenin, and that's going to be this voltage drop across the 60 ohm resistor. So we have two options here. We can use the node voltage method or the mesh current method. The method that I chose is the mesh current method because we all have our quirks. And my particular quirk is that I don't like to do the node voltage method when I have a voltage just hanging out in the middle. I kind of like it when things are neatly at the node. So, and that's just my particular quirk. So I chose to do this with the mesh method. However, that being said, you can do this with the node voltage method. I would definitely challenge someone out there in YouTube community to post a reply video with the solution solved using node. So let's get started. I choose the mesh method. That means I have some, let me just make sure that I label my mesh currents the same so I can cross-check myself. So this I called IA, this I called IB, and this I called IC. Okay? So we're going to use the mesh method, and just to give you a preview, we're looking for this voltage drop. That's our Thevenin. So I know that once I find my IC mesh current, the Thevenin will be the 60 ohms times the IC. That's my goal. That's my strategy. So mesh at IA gives me 5 times IA minus IB plus 20 IA. And then here we have a current source, and so the direction of the voltage rise is from here to here. So I'm going from minus to plus, and there's some Vx voltage drop there. Okay, now if you were super duper clever, you would say this border is a current, and since it's a current, I have a super mesh, and so I could just go around here like that and write my equation. But if you were in a rush and you didn't immediately see that, that's okay. What you would do is just give this a voltage, and remember that the mesh method utilizes the KVL, Kirchhoff's voltage law. So then this voltage drop here is some unknown Vx, so we're going to go plus Vx. So we have 3 drops, and all that sum is equal to 0. So mesh at IB then. So here we have 9 volts, so minus 9 volts is the first voltage drop we see. And then we have 5 times IB minus IA. And then plus 25, that's going to be times IB minus IC. That's equal to 0. And then our final mesh is at IC. So we got 25 times IC minus IB, and then we have this voltage right here, minus Vx, and then plus 60 IC and plus 10 IC, that's equal to 0. Okay, so at this point, we could eliminate the Vx if we add these two together. So in algebra, we are allowed to do that. We can add any two equations together. So if we wanted the Vx's to cancel out, we could do that. But if you didn't see that, you'll still be fine. Because right now we have IA, IB, IC, and Vx. We have 4 equations, 4 unknowns and 3 equations. We need to come up with one more equation. So the 4th equation is going to come from the constraint equation. So we have the current source is going in this direction. That means IC will be the positive number, or the positive current. So our constraint equation is going to be IC minus IA, and that's equal to 1.8. Okay, so far we're doing just fine, even though we didn't see that this was a super node or a super mesh, and we also didn't see that we could add these two to eliminate Vx. We still came up with 4 equations and 4 unknowns. So let's make our matrix. We have IA, IB, IC, and Vx. Okay, just take it a second and make sure. Okay. So let's start inventorying our coefficients. So now we're going to inventory the coefficients, and so we got the first mesh equation. We got 5 IA, and then minus 5 for IB, and then 20 plus 20 for IA, and then plus 1 for Vx, and then 0 constants. So that's going to be our first line in the matrix. And then at IB, we have a -9, which is going to go on the side of constants as +9. And then we got a 5 for IB, -5 for IA, plus 25 for IB, and then minus 25 for IC, and then 0. Okay, so then mesh at IC, we're going to have 25 for IC, and then -25 for IB, -1 for VX, and then 60 plus 60 for IC, and then plus 10 for IC, and then we got zeros everywhere else. And then our last mesh equation is going to have 1 for IC, -1 for IA, 0, 0, and then 1.8 for constants. Right, so now we're going to put that information into our scientific calculator and into our simultaneous equation solver. So we got 5 plus 20, and then -5, 0, 1, and 0. And then we got -5, 5 plus 25, -25, 0, and 9. And then we got 0, -25, 25 plus 60 plus 10, and -1, 0, -1, 0, 1, 0, and 1.8. Solve. Okay. Alright, so I didn't get the right answer, so let me double check. Oh, went too fast. Okay, so I got 25, -5, 0, 1, and 0. Okay, that line is correct. Oh, the rest is all messed up. -5, and then we got, oopsies, -5. Then we got 5 plus 25, that's 30, -5, 0, and 9. That line is correct. Third line is 0, -25, 95, 1, and 0. That line is correct. And then we got, oops, okay, so my fourth line has a mistake. 1, 0, and 1.8. Oh, and I just want to let you guys know that it's easy to make mistake with simultaneous equations, so just double check everything. So anyways, I did this when I was solving it as well. It took me a while to find my errors, a plus, a minus. Okay, I'm gonna double check it with what I got before. Okay, so that matches up with what I got the first time, and that ended up being the right answer. So, what you should have got when you solve your simultaneous equations is, you should have got IA is -1.3 amps, IB is 0.5 amps, IC is 0.5 amps, and VX is 35 volts. Okay, so like we said originally, that was our strategy, was to find IC, and since the Thevenin is the voltage drop across the 60 volts, we have Thevenin is going to be 60 times IC, and that's 60 times 1/2 an amp, so that's going to be 30 volts. So we found 1/2 of it, so let's park that value here. Thevenin is 30 volts. That's 1/2 of the Thevenin equivalent circuit. Now we need to find our Thevenin. And strategy A, we're going to do this by strategy A, strategy number 1, which the book told us to. In part A, we needed to do it by finding I short circuit. So we're doing R Thevenin is equal to V Thevenin over I short circuit. So I short circuit then is basically shorting the load, and then finding, shorting the load, and then, and finding the short current. So we're going to short the load, and then we're looking for this current, I short circuit. Alright, so let's start over. We still have some Vx here, so I'm going to leave that there. Some Vx there. So now, this is still 1.8 amps. So now once we short the load, we have a short, right? So 0 in parallel with 60 is going to be 0. So we shorted out this 60 ohm. It's no longer a factor. We're looking at current that's going through the load. So again, I'm going to use the mesh method for the same reason. So I have IA, I have IB, and I have I short circuit. Okay? So let's rewrite our mesh equations. Now that the 60 ohm resistor is no longer a factor. So mesh at IA is going to be 5 times IA. So we have 5 times IA minus IB plus 20 IA, and then so plus Vx, that's equal to 0. So the equation is still the same. So then mesh at IB, that's going to be minus 9 plus 5 times IB minus IA. And then plus 25 times IB minus I short circuit. All that is equal to 0. So now we're going to write our mesh equation at I short circuit. And we have 25 times I short circuit minus IB. And then that's going to be minus some voltage drop Vx minus Vx. And then this was a 10. And then plus 10 I short circuit. That's equal to 0. And then we need a fourth equation, and that's going to be our constraint equation. So our constraint equation is going to be I short circuit minus IA is equal to 1.8 amps. Okay, so now we're going to write our matrix. IA, IB, I short circuit, Vx is equal to. And then we're going to start inventorying, taking inventory of our coefficients. So the first equation we're going to do is the constraint equation. We have a coefficient of 1 for I short circuit, negative 1 for IA, and 1.8. Zeros everywhere else. Okay, so mesh at IA we have 5 for IA, negative 5 for IB, plus 20 for IA, and then 1 for Vx. In the mesh at IB, we have a negative 9 that's going to go on the side of constants as positive 9, and then 5 coefficient for IB, negative 5 for IA, and plus 25 for IB, and then minus 25 for I short circuit, and 0 Vx's. And then so mesh at I short circuit is going to have a 25 for I short circuit, negative 25 for IB, negative 1 for Vx, and 10 plus 10 for I short circuit, and then zeros everywhere else. So now we're going to input this information into our simultaneous equation solver. We have 4 equations and 4 unknowns, so we have negative 1, 0, 1, 0, and 1.8. Then we have 5 plus 20, negative 5, 0, 1, and 0. Negative 5, 5 plus 25, negative 25, 0, and 9. 0, negative 25, 25 plus 10, negative 1, and 0. Solve. Okay, double check with what I got the first time around. Okay, so that matches what I got the first time around. So I'll post what I got. So when you solve this system of simultaneous equation, you should come up with IA is negative 0.3 amps, IB is 1.5 amps, I short circuit is 1.5 amps, and Vx is 15 volts. We're looking for that. So we have I short circuit is equal to 1.5 amps. So now we're going to use method A of finding R Thevenin, and that is V Thevenin over I short circuit. That gives me 30 divided by 1.5 amps, 30 volts. So we got 30 divided by 1.5. So that gives me 20 ohms. Okay, so then the answer to part A is going to be, that's going to be plus minus 30 volts. And then 20 ohms, A, B. So that's our Thevenin equivalent circuit. And just in case you get asked for the Norton, we just do a source transformation. Remember V over R, so 30 divided by 20. And of course it should be our I short circuit. So we could do a source transformation, or we could just say that that's the same thing as our I short circuit, 1.5 amps in parallel with 20 ohms. That's just in case you get asked for the Norton equivalent. Just realize that the Norton equivalent and the Thevenin equivalent circuit are just source transformations of each other. So whatever you get asked for. Okay, so that is part A. Now part B says to find the Thevenin resistance the alternative way, without V Thevenin or I short circuit. And to do that, we restore the circuit. So let's restore the circuit. It looked like that, and then we had 60 ohms right here, and here was our load, AB. That's what the circuit originally looked like. So now, what we're going to do is we're going to do this without V Thevenin and I short circuit. So that means we're going to remove the effects of the power sources and ask, what does the load see? What resistance does the load see? So to remove the effects of the voltage sources, we short them. So we're going to short the 9 volts, and then to remove the effects of the current sources, we open them. So we're going to open that. And then we're going to ask ourselves, what if we were to stick our ohm meter right there, what would we see? What resistance would we see? So, so the first thing that we can do is realize that this is really, let's start simplifying the circuit. So an easy thing to see, this is a little harder to see. This is harder to see, like what's happening here. But this is easy to see. We can see that 5 is in series with 25, so we can replace that with a single resistor of 30. 5 plus 25 is 30. And then now it's a little bit more simplified and easier to see. So now we see that 30 is in parallel with a short circuit, and 30 in parallel with a short circuit is going to be 0. So now we can see that 60, so this is in series with that, right? So this is 20 is in series with 10 gives me 30. Now what's the relationship of 30 with respect to 60? It's connected to one end. So 30 is connected here, and then the other end of 30 is connected to 60, the other end of 60. That means we have 60 in parallel with 30. So 1 over 30 plus 1 over 60, inverse that, and that'll give you 20 ohms. So that checks. And that's the answer to part B. Alright, you guys, make sure to like the Facebook page or share the video if you got help from it. Thanks.